My name is Eugene, and I'm working on XLA, and I will be talking about XLA architecture at a high level, how XLA works, what are the important pieces in XLA, and basically what makes XLA XLA, the important design decisions that were made many years ago, and they were mostly right, and that's what allowed us to build successful backends for multiple hardware. So, what is XLA? It's a compiler. It takes some intermediate representation and compiles it to executable that runs. And this is compiler designed for accelerating linear algebra computations, and that's why it's called XLA, accelerated linear algebra. So it's very simple input language, mostly focused on dense linear algebra operations on multidimensional arrays. It used to be tensors in the TensorFlow era, but in XLA it's called arrays. It was originally designed to program TPUs for TensorFlow. Like I think the first integration was done into TensorFlow to target TPUs, but because of all the design decisions, it works remarkably well for GPUs, CPUs, and other hardware accelerators. And what's important, it's not really a product, a Google product, and no one really targets XLA directly. It was designed to be targeted by ML frameworks, and end users write Python in the framework of their choice, and somewhere behind the scene, XLA does all the job. So it was designed for TensorFlow and compiling TensorFlow programs. Then it was ported to JAX. So JAX was basically started as just AutoGrad and XLA. So some simple way to target XLA without all the heavyweight parts of the TensorFlow. And now we focus also on the PyTorch to make XLA a good backend for the PyTorch. The key decisions that were made by XLA in the early days. So it's reduced ML instruction set compiler. The offset is very small, about 100 operations. So in TensorFlow era, we had kernels, and we had hundreds and thousands, and I think right now in Google we have multiple thousands of kernels. And we recognize that it's just impossible to write a compiler for all the thousands of kernels, and the number of kernels keep growing up. So it was a deliberate decision to pick a base offset that can express any interesting ML program and be very careful what operations added to the offset. I think PyTorch these days has the same problem. A lot of PyTorch operations, a lot of handwritten kernels, and the offset keeps growing. Another decision was statically shaped input programs, because if you want to reach peak performance on your hardware, you have to know perfectly well what are the sizes of all your data, because you have to register assignment, do memory assignment, planning. And this was working really well in the past, but these days it's changing because of mobile. We want to target different hardware generations and text models. In text models, your sequence length is usually dynamic. You can do padding, but you waste a lot of resources. Or if you want to do on CPU, it's very easy to compile dynamic programs on CPU, and also quite easy on GPU. So I think the statically shaped input programs was mostly because of how TPU works. But this is changing. So as you've seen earlier in the keynote, we will be adding dynamic shapes and symbolic dynamic shapes to the StableHLO, and eventually it will get full support in the compiler backend. And also about reduced instruction set, this is also changing. So the fact that today you can't represent different fancy attentions with a basic offset. So you can, but it will be very inefficient. So that's why at StableHLO level, we have composites that allows you to plug in high-level concepts into XLA, some fancy attention, and if you have a custom kernel for fancy attention, you have some decomposition into the base offset. The next thing is static operation scheduling, also because of how TPU is designed. So TPU is basically single-threaded machine with giant registers and enormous matrix multiplication unit, and it doesn't have multi-threading or multiple cores. So that's why XLA assumes that you can always statically schedule operation. But that's not really true on the other backends. So for example, on GPU with multiple streams or on CPU with multiple cores, you can schedule multiple operations. So XLA still relies on static operation scheduling for compile time, mostly for the memory planning, so the next point. But at runtime, different backends can rely on the memory conflicts. And basically, if you have two operations that don't have memory conflicts, and if the underlying hardware can run them concurrently on NVIDIA GPUs, multiple CUDA streams or CUDA graphs, on CPUs, it will be multiple cores, we will run them concurrently. And operation scheduling is static, but you can optimize for minimum memory. So for example, TPU has a very small memory, and memory is expensive, same on GPUs. So you optimize really hard for minimum memory overheads, but on CPU, memory is pretty much free, and you optimize to, you have to build a schedule that maximizes available concurrency, and you can use any memory you want. And another decision that was made by XLA that we have front end and multiple backends. So HLO, high-level operations, high-level optimizer, is the XLA front end that is shared by all the backends. And every backend has, so front ends are mostly the same, so they compose from the same HLO level passes. On TPU, we have TPU-specific HLO passes that are closed source, but as I've heard earlier, they will be open source in the future. Well, backends, TPU backend is private, GPU and CPU backends are public. So most of the difference in between XLA backends in this second half, how exactly, what is the machine code, what is the underlying architecture, and how do you code gen from after HLO optimizations. Concat will be static, so compiling something like where will produce the dynamic shape, but what you will have padded to the maximum size, and then at runtime, you will code gen for the true dynamic size of the data. In XLA, so in TensorFlow in PyTorch, you can concatenate based on the dimension that is defined by the runtime value. In XLA, you can't represent that. In XLA, concatenation is always done on dimension that is known statically. That's why you can derive your output shape from input shape.
How about batch size, which is usually a variable?
We do padding. So what happens in practice, you do padding or you do bounded dynamism, but usually padding. Padding, you accumulate up until some batch size and compile for some powers of 2, and then you do padding. Yes. So once compilation is done, you know 100% precision what will be the memory requirement for a program, and you know that you will not run out of memory. So if you were able to allocate your arguments, and you can allocate your scratch memory, temp memory for all your intermediates, we know this program will finish execution until, or unless you have some exception or something like that. So in XLA, you have to know. So in XLA, everything has to be statically shaped. So it's nice in the sense that you get very predictable results. You don't get variance. So the same, if you run the same program on the same hardware multiple times on TPU, you will get exactly the same results. On NVIDIA GPUs, you also will get roughly the same results. On CPU, is a lot more variance because memory bandwidth, caches, threading, kernel. But this design, or XLA was designed for predictable latency and predictable number of cycles on TPUs. And it does really well with everything is statically planned ahead. So XLA operation set. So StableHLO is the input language. This is a Maliar dialect with a specification and backward compatibility guarantees. So all the frameworks these days, they target XLA by emitting Maliar modules with StableHLO operations. So if you can think of XLA as a virtual machine, this is the language of the XLA virtual machine. And this is targeted through the PGRT API. So basically, the PGRT API has two main functions. Compile, you pass StableHLO module to compile, you get back some executable. Then you have some kind of buffers, which represent multidimensional arrays in device or host memory. And then you can take your PGRT executable, execute it, and you get back new set of buffers. And XLA and PGRT, the important thing that buffers are immutable conceptually. So you pass values as arguments to your executable, and you get back new values to executable. You can do donation. to do in-place updates, but this is a very big departure from how PyTorch does things. So in PyTorch, buffers are mutable, and you can manipulate strides and slices basically free. So slicing in PyTorch, you just manipulate strides and you get back a new buffer into the same view, into the same memory array. In XLA, because all the values in XLA are densely packed, so if you do slices, dynamic slices, you have to move the memory around. But XLA, because it's compiler, it can fuse your slices into other operations. So in practice, you should be almost never materializing your slices. So it should be free. So this is an example how JAX program, very simple JAX program, looks like in StableHLO MLA format. Very simple function, a plus b divided by a multiplied by b. Very simple element-wise functions. So we do just compilation, which creates trace JAX expression, which is not shape specialized. So when you do lower and you pass a and b with a concrete shape, this is the time when JAX specializes JAX expression to this particular shape. And then you can see the compiler IR in StableHLO DevLab. So it's very simple MLR module at the top level, container for the function. You have the main function, and you have two tensors as inputs, and shapes are fully static. 3 StableHLO operations, and then you return the result. And the StableHLO offset is pretty small. It roughly corresponds to the internal XLA HLO offset, 100 operations maybe at this time. But XLA, internally, it doesn't really use StableHLO for compilation. So almost immediately, once StableHLO passes from JAX to XLA, we do conversion to HLO, our internal representation. So I think the reason is mostly historical, because XLA was developed 10 years ago, before MLIR existed. So we have our own intermediate representation, which is inspired by the original LLVM IR, but it doesn't share anything with LLVM, so it's completely separate code base. It has, I know, slightly nicer pretty printing. You don't spell tensors explicitly. You have shapes, dimensions, layouts, and instead of arguments, you have parameters. Functions is not like a concept in the IR. It's called computations, but they look like functions. It's not tensors, it's arrays. So I think tensors is the artifact of TensorFlow, and MLIR decided to call things tensors, but it's really arrays in NumPys, arrays in JAX, arrays in XLA. And because almost everything is array, remember XLA is a language for accelerating linear algebra. Every temporary, every intermediate is array, so you don't have to spell it. You just spell the shape, and you know that's an array. And it doesn't support returning multiple values. So that's why we have tuples, and I think this was inherited from LLVM. LLVM also doesn't support returning multiple values. You have structs, and that's why we have tuples. But at this point, most of the new development happens in the MLIR land. So StableHLO for the offset as an input language. Dynamic shapes, symbolic shapes, they also will be done in MLIR land. Sharding is done in MLIR. Quantization components. So I think more and more new stuff gets developed in MLIR, and over time we expect more optimizations to be implemented in MLIR, because that's what the industry and the people prefer. And the tooling in MLIR is, and I would say, some tooling is better, some tooling is worse. So we have in ideal world, we'll standardize on one set of tooling and dialects, but it will be a very slow process because we have 10 years of development in HLO and HLO optimizations. So the main concept in XLA is array shape. So you have the data type, then you have dimensions, and the important thing that we don't have in StableHLO is layout. So input to the XLA, so it comes in data flow, value semantics, form, and later during compilation, it becomes closer and closer to hardware. So the input usually will have F32 and dimensions, and the layouts, they might exist in the shape in the input program, but usually they don't. But once you have to do compilation for your hardware, you have to know how the data is laid out in memory. So it can be a row major, it can be a column major, it can be, for high ranks, you can shuffle dimensions. And also for TPU, you can do tiling and memory space assignment. So basically, the initial shape that you get in your input program is very simple, but it gets more and more complicated the closer you to the hardware. So yeah, layout, one of the things. So layout is a permutation of your dimensions and how your dimensions are physically stored in memory. So it's from the minor to the major dimension, from the fastest changing to the slowest changing dimension. And it has the same rank as the rank of the tensor array in dimensions. So 1, 0 is, this is row major, because the last dimension is contiguous in memory. 0, 1 is column major. It's quite hard to understand because I think it's reverse what every other framework is doing. But once you get it, you get it. But you lose this information like very, very quickly. But basically, this is kind of strides. You can represent the same information with strides, but XLA decided to represent that information with dimension permutation. And the same with tiling. You can represent, so one option, so you have this two-dimensional rank 2 shape, and you have dimension order that defines the layout, how dimensions laid out in memory, but then you define tiling, how they are tiled. So there are multiple options. How do you present shapes like that? So one option is to introduce a rank 4 array with strides. And I think that what would PyTorch do, and some other frameworks, if you want to define how, or some other MLR dialects, Linux, for example, what it goes for higher rank tensors and strides. XLA represents tiles and layouts more explicitly in the shape. So it's easier for human to see the original tensor, the original shape, because it usually corresponds to the user program. And over time, once we do lowering for the concrete hardware, you can select tiles based on the sizes of your registers. And there are only a few tiles. So for example, TPU has a couple of shapes of registers, and like 128 by 8, 128. So some of that is described in Palace documentation in JAX. So how to write an efficient kernel in Palace. And they go into details like what are the sizes of the registers in CPU, what are the memory spaces, and how to efficiently select the tile size. On GPU and CPU, we don't use tiles at all because we don't really need to. So we can do tiles for the code gen, but we can do, so on GPU side, tiling happens during the code gen. So everything is row major, almost everything is row major. Same in CPU, almost everything is row major. Few things are column major. If you want to do vector matrix multiplication, you can do column major because you get linear memory traversal. But because on CPU and GPU, you get byte level memory access and registers 1, 2, 4, 8 bytes, you don't have to do any tiling. Because what happens on CPU, you have the register 128 by 8. And basically, tile assignment simplifies the code gen later during the pipeline. You load one register at a time from the memory. So one tile corresponds to your register. Yeah, I think even in memory. So you have some tile, you have some garbage in memory. You load some garbage in registers. You compute some garbage. You write garbage back. But once you move the data back to host, you do conversion to row major usually, and you throw away all the garbage in the padding. So you never use padded values for anything useful. So as long as it doesn't trap or introduce some invalid computation, it can be any undefined sequence of bits in the padded values. Why we need tiling? Mostly because of how the TPU is designed. So Palace documentation, JAX, it goes into some details, array layouts, and register sizes, and that's the main reason why tiling was introduced to XLA in the first place. On GPU, I think it might be useful in some cases if you want to do tiling and you do code gen for matrix multiplication units, tensor cores, then GPU becomes more like CPU, but it's all hidden because on GPU we can do memory transfer into shared memory or the tensor memory that does automatic tiling for you. So there is no need to represent tiling at high level. Tiling is implementation detail of the CUDA kernel, Catalyst kernel, Triton kernel, or basically inside the PTX. Because the memory copy, async memory copy in CUDA, it can take the base pointer plus tries and copy the tile with the data into the shared memory. You don't have to keep your data in your HBM in the tile format. Although maybe if you would do that, it would be faster. I don't know the details, how fast, like if strides impact the memory copy performance on GPU backend. So we have other shapes, tuples. As I mentioned, we don't support returning multiple results. So if you want to return multiple results from your operation or computation, this will be a tuple. And tuples, they do support arbitrary levels of nesting. And tuples, they don't have physical representation usually. It's just symbolic. We do buffer assignment, so every array inside the tuple gets some region of memory on device. In some edge cases on CPU, tuples act as buffer tables when we hit some limits, but it never happens on GPU and CPU. So on GPU and CPU, it's only symbolic inside HLO, and every value assigns some memory space and memory address in the allocation. We also have tokens. They used to represent control dependencies as data dependencies. So remember that HLO input language is a data flow. So everything can be executed as ready, and compiler is free to reorder operations and execute them in any order. But if you want to force compiler to execute pair of operations or sequence of operations in one particular order, you have to create and thread tokens for all operations. This is important, for example, for collectives. If your collectives implementation requires that all collectives on all ranks, they launch in the same order. For example, this is the requirement of Nickel. You can't launch collectives in random order, it will deadlock. In this case, XLA GPU uses tokens to connect all the collectives together. So no matter how you compile your executables, the collectives will be executed in the same order on all ranks. So XLA itself is deterministic. So if you compile the same XLA program on multiple ranks, you should be getting deterministically same results and same order of all operations. But we do still have bugs, and that's not always true. And tokens is a user mechanism that forces that. Yes?
But you also have control dependencies.
Control dependency is an internal implementation of HLO. So you can't create stable HLO program with control dependencies, and you can't create HLO with control dependencies. This is something that XLA itself during compilation process can add, but it's not a user visible feature. So tokens is a way to express control dependencies accessible to the user, to the front end. Control dependency is the implementation detail of XLA. So XLA might decide that we want to guarantee that these two operations run in this particular order because we know that we have some resource constraints or memory constraints, or something like that. And then we add control dependencies because not all operations have tokens as arguments and results. Only side-effecting operations have tokens as arguments and results. Yeah, basically tokens only support the side-effecting things that I think collectives, in-feed, out-feed, and I think that's all, because everything else is supposed to be, so remember, XLA, HLO is a pure language, pure data flow, immutable values, everything nice and should be able to execute in any order. So that's why most of the operations, they don't have tokens. Only the things that can touch the outside world network for collectives, only those operations have tokens. Everything else is a pure computation, some bytes in, some bytes out, and it doesn't matter in what order you execute it. And we also have opaque type, but I don't think that it's ever used. the idea was that you can pass a voice star pointer to XLA, and XLA will forward it to a custom call, and then you know what's in your voice star pointer. And we have a type, because you don't want to pass unsigned 64-bit scalar around, because it's confusing. So opaque is backend-specific opaque pointer that you can pass around. But I don't think that we have many users or any users at all. Definitely no users in CPU and GPU backend. As I mentioned, so XLA relies on the fact that all the dimensions are known at compile time, and you can do memory planning. You know how much memory you need, and you can generate your code. Basically, all the loops have static dimensions, and you can statically decide when you want to unroll the loop and not to unroll the loop. But if you don't know the dimensions, XLA supports bounded dynamism. So less equal, for example, F32, you know that the shape of the array is smaller than 128 and 64, but the concrete value is unknown until the runtime. So at runtime, you will get the buffer 128 by 64, and after the buffer, you will have two scalars that define the real size of the buffer. And the code gen will emit machine code that will respect the true sizes of the buffer and compute data only in the relevant part of the array. So you'll get, so in the ideal world, we don't even touch the data outside of your real dynamic bounds. In some cases, when it's impossible, we can do padding and compute some garbage on these padded values and then slice it back to the real shape. The downside, that you pay the memory cost of your full shape. But you can avoid the compute cost if you don't compute on your padded values. And it has a good support on CPU backend. It's not supported on CPU backend, I think, and GPU backend also has like partial support. So the most common use case for XLA is fully static shapes, although bounded dynamism can be represented. We'll see how StableHLO and symbolic shapes will work together with that. Eventually, I guess we'll have to support symbolic shapes in HLO as well. And this is how HLO instruction in HLO presentation looks like. So you have the name, all instructions have names. This is the big difference from MLIR and SSA values. When you have random numbers, it's nice that you can preserve some meaningful names from the framework. You have the output shape, opcode, the code of the operation, operands, and then you have some set of attributes. And in contrast to MLIR, HLO offset is closed offset, and that's why it can be pretty printing is much shorter than MLIR, and it's much easier to parse, but conceptually idea the same. XLA programs compose from computations. In the MLIR land, there will be a function. In C, C++, this is a function. You have parameters, so you don't spell parameters in your brackets in your function definition. You have parameter instruction in your computation body. That's how you know the parameter index and the shape of the parameter. You can produce only one value, and if you need to produce multiple arrays, then it has to be a tuple. And we don't support recursive computations, because what happens at compile time, we inline and flatten everything and create a flattened call graph, because we need to do static memory planning and static scheduling. So it is impossible with recursive computations. That's why you can't express them in HLO. It will just fail verification. And the top-level computation is entry computation. It's your main function. That's how you pass your arguments parameters to a program. And entry computation defines the layout and the results of your main function. So everything is passed as a buffer. So XLA itself doesn't allocate any memory. The assumption is that executable that XLA is compiled takes buffers for parameters. It takes a buffer where to write the result. It can be the same if parameters alias with results. And it also takes a pointer to the temporary allocation. That's where XLA slices at different points of execution of the program. It slices temporary allocation and keeps the temporary values. So everything is allocated ahead of time by the host runtime. And another important property of XLA that parameters and outputs of control flow computations while conditional call I think they are alias. So for the while input, yeah, because the shape of your tuple of the argument of the result must be the same, and the location must be the same, because it's important how you execute multiple loop iterations, and you might see some accidental copies inside the while body that are required because of how memory allocation works in aliasing. So I'll go a little bit in details of the XLA compiler structure and front end. So we have a front end that does mostly backend agnostic optimizations, and front end is a set of transformations from HLO to HLO. And series of passes, every backend, every TPU, GPU, and CPU backends, they create the compilation pipeline from mostly the same set of passes in different order. Some of the passes run like fixed point iterations. So a lot of the passes are device independent. And the backend generates machine code. So once we've done with the high-level optimizations and we have optimized HLO, then we pass it to the backend, and backend emits machine code for the HLO and doesn't touch HLO after that. And backend's very device-specific, so we share some of the details, emitters. So it's usually called emitters. You take an HLO instruction, HLO fusion, and you emit machine code. We do share emitters between CPU and GPU, where it makes sense, because CPU and GPU architecture is, you can pretend it's the same. You have CUDA, you have multidimensional grid on CUDA. On CPU, you have multiple cores and multidimensional loop nest, but what's inside your loop nest is the same. You have registers are the same, like 1 to 4 bytes, YOLO, byte addressable memory. You emit the same LLVMIR. On TPU is very different because register sizes are different, ISA is very different. But conceptually, what backend does, it takes HLO and produces backend-specific assembly. On GPU, we have auto-tuning database. So we do auto-tuning ahead of time, and we have a database. So you can, instead of running computation during compilation, we have a database that can tell you what are the best choices styling, for example, for different matmos for Triton. On TPU, cost model. Yeah, so on TPU is mostly cost model, and on GPU as well. So it's cost model plus an auto-tuning database. Yeah, so XLA does layout assignment because XLA itself knows the hardware. It knows what's the optimal layout. So XLA does layout assignment and future decisions based on the knowledge of the underlying hardware and the cost model of the underlying hardware. And it tries to make good decisions. So generic optimization passes, simplification, algebraic expression simplification, common sub-expression elimination, inlining tuples, co-inlining dead codes. So very backend agnostic. Multi-device optimization, sharding. So input XLA programs, they are, you can write in JAX, for example, one program that will be executed on hundreds of thousands of devices, and XLA is responsible for sharding your input program into multiple programs that will be executed collectively through SPIM departitioning. There's a sharded talk, will be later. So if you're interested about sharding, I recommend to go there, and they will go into the details. Scheduling instructions is also backend agnostic. You want to schedule instructions to minimize memory or maximize concurrency. Basically, you have a cost function that you optimize for, and you can try different strategies for scheduling operations, deciding in what order operations should be executed based on your cost function. And cost function can be how much memory do you use, or cost function, how much concurrency is available after scheduling, how many operations can be executed in parallel. So if you have two matmos that don't share any data dependencies, you might be able to compute them in parallel if they're small. If they're huge, it doesn't really make sense. You can save some memory and compute matmos sequentially, and maybe try to overlap your computation with something else, but it's only applicable for CPU and GPU backends. On TPU, everything is single-threaded, and you always optimize for the minimum memory. And fusions. So fusions is grouping operations together that will compile to the single kernel. The idea of the fusion that you read your arguments parameters to a fusion once, and you keep them in registers, and then you write your registers back to the memory once, and you group your operations together. That minimizes the memory bandwidth and optimizes compute utilization. So most of the passes are optional. You can not run any of the passes and compile input HLO to machine executable machine code in the end. It will be very slow, but it should work, and I think it usually works. So yeah, partitioning. As I mentioned, so Shardy is the new one that is done as a collaboration of X, Google Brain, GSPMD, and part IR implemented by DeepMind. So two teams bring together best of both worlds and implement partitioning, compiler passes, and IR for SPMD in Shardy, and also MPMD is coming. And GSPMD is something that was done in XLA originally a couple of years ago. It works on HLO representation, and it has a couple of limitations. It's very complicated. It's very hard to understand. So Shardy is the new shiny thing that is much easier. And if you're interested in partitioning, I recommend to look at Shardy. Although GSPMD paper is pretty interesting and very easy to read. So fusions. What's the main point of fusions? When you read the first element from array, memory latency is very high. Same on GPU, CPU, TPU. So all hardware is roughly the same. You have the memory that is far away and very expensive to fetch data. You have L1, L2 caches on GPU and CPU, VMEM on TPU, so slightly more explicitly managed on TPU, implicit on GPU and CPU, but the idea is the same. You want to execute load from memory once and execute as much as possible compute cycles on the data, and then write data back. So that's the main reason why we have fusions, and that's how XLA gets all the performance improvements. Layout assignment. So it's mostly important for TPU because of the hardware shape and shape of the registers, but it is also important on GPU and CPU. For example, if you do matrix multiplication or transpose, linear memory access is important on all hardware. So you always want to keep your data in memory in a way that will allow your hardware to read data linearly, because reading with a stride can be 10 times slower on all backends. And also, not all code gen strategies support all layouts. So I think it's mostly important for things like matmos when you stream. So element-wise operations, it doesn't really matter. You can read memory. So shape doesn't really matter. It gets important for reductions. So you want to read reduced dimension linearly. It gets important for matrix multiplications, matrix vector multiplications. So XLA tries to assign layouts to all intermediates to optimize the performance of the code gen, and it inserts transposes between layouts in the middle. So copy insertion. Remember that StableHLO and input HLO has value semantics, and PGRT, the runtime, also has immutable value semantics. But what happens at runtime, you have buffers, and you have mutable memory, and you have scatter dynamic update slice. So at HLO level, you have a scatter. You take your big array, and you scatter small number of values at different positions in the big array, and you get back a new array, which is a copy of your original array with some values updated with your scattered values. And that is the semantics of your StableHLO and HLO. But that would be super wasteful if that's what would happen at runtime. So really, in practice, you have a buffer that you mutate in place. But it means that if you use the original buffer multiple times after scatter operation, you have to insert copies. And the same for control flow. It's very similar to finals in SSA representation. So copy insertion is very important, that it does global program analysis. And when you go from the immutable value land into the mutable buffer land, when the transition happens, copy insertion inserts copy operation that guarantees correctness. And it might not always properly see all the mutations. And what often happens, you end up with more copies than required. I think originally copies were done at computation level. Right now, XLA can do copy insertion and copy lesion based on the whole program analysis. But I don't think that's enabled by default. So if you see copies, you know that in the input program, copies, they don't really exist, because if you have immutable values, why would you need a copy? Your value is immutable. So I don't think that, I don't even know if StableHLO has a copy operation. Probably not, because why would you have it? But the closer you get to the hardware, then you might get copies. And buffer assignment. So the important thing of buffer assignment, you have these values, which kind of immutable, but really we want to convert from immutable values, immutable arrays, to mutable destinations in memory. So what happens, you pick some execution order of all operations, and you compute a live range for all your values. And based on the live ranges, you can do buffer assignment. And buffer assignment means that at this particular point in your program, this value can live in the slice of your temp allocation. And temp allocation is a giant scratch that keeps all the temp arrays. So parameters and results, they have their own allocations managed by the higher level runtime, but all intermediate values, they are inside temp. So you have, it's based on data flow analysis. So it's basically the step from values to buffers. So, and the last thing is code gen. So what you get in there, so this is the original program, JAX program, with addition, multiplication, and division. So that's what you get for CPU and GPU. You have a single fusion computation with all operations inside the body. And it means that you load parameters once, you do addition, multiplication, division, and then you write back the result. And your entry computation has a fusion node, which calls fuse computation. And it's identical for CPU and GPU. For TPU, it's slightly different. So you have fusion and single fusion. Tiles are explicit. You see that this is one-dimensional tensor, and we tile it by 128, because the size is 128, so it has to be at least 128. And also, second parameter has S3. This is the memory space. This is VMem memory space, fast vector memory. So on TPU backend, XLA compiler decided to prefetch one of the parameters into the fast memory, and it has a copy start and copy done operation. So for this particular program, it's not really needed, because immediately after copy starts, you do copy done. But for something more complicated with multiple fusions, XLA will try to prefetch memory from slow HBM to fast VMem when it can. Because on TPU, memory copy operations, they are more explicit than on CPU and GPU. So on CPU, you don't really manage your caches. You try to emit code with the linear access, and then you hope that you will hit the L1, L2, but you can't force CPU to keep data in L1, because your thread can be migrated to different core, things like that. Same in GPU. You have shared memory, but you can't reuse shared memory between different CUDA kernel launches. So you can't prefetch something into the shared memory ahead of your CUDA kernel launch. You can do prefetching inside the CUDA kernel, but it's not visible at HLO computation level. TPUs are different, so memory operations are more explicit, and you can see some copy operations between different memory spaces in the optimized HLO. And then in the end, we compile every fusion to a kernel. So for XLA GPU, kernel is basically LLVM IR with PTX intrinsics. So on XLA GPU backend, we produce LLVM, and then we use NVVM, DirectX NVIDIA LLVM backend to compile that to PTX, and then we pass PTX to PTX AS, and then we get SAS, which is NVIDIA assembly, and we load NVIDIA assembly on device. So the signature of the kernel is very simple. You pass every buffer, every XLA array, you pass as a pointer to your PTX main function, address space, intrinsics to get your grid position, and things like that. And we always, on GPU backend, we always produce LLVM IR with this ABI, function signature, from fusions compiled with our own XLA emitters. We have two versions, two versions. One of them, I think most of the kernels these days produce with emitters based on the new MLR pipeline. And the same happens with Triton. So if you write a kernel in OpenAI Triton, eventually it gets lowered to LLVM-IR with PTX, NVIDIA intrinsics, and then you get PTX and SAS and loaded on device exactly the same way. XLA CPU kernel is also LLVM-IR. Very simple. You have a kernel call frame, which is you have the number of workgroups and workgroup ID, which roughly corresponds to CUDA block dimensions and block ID. And you get your position into your multidimensional grid. And multidimensional grid on CPU backend is launched as multiple threads. So you can imagine on CUDA backend, if you have multiple blocks and block execution is managed by the CUDA driver and the NVIDIA GPU itself. For the XLA CPU, every block corresponds to a task submitted to a thread pool. So programming model conceptually somewhat close to GPU, and LLVM-IR that we emit also somewhat close to GPU. You get some pointer to a call frame. From that pointer, you get the information, you get the pointers to buffers, and you get your position in the multidimensional grid, and then you execute a tile of work, mutating the data and writing data back. And both on CPU and GPU, the trick is to read memory linearly on GPU to get memory coalescing, on CPU to get memory prefetching, and to write memory linearly. Again, memory coalescing and prefetching. So we try to make hardware happy by reading and writing memory linearly all the time. This is the big difference from TPU program. We don't really have kernels in TPU program. So you take this whole optimized HLO graph and emit one giant binary that gets loaded to TPU and executed fully on CPU. The big distinction that XLA GPU host drives computation. So we invoke kernels by invoking CUDA APIs, and model inference can take thousands of kernel launches. And if you have some big LLM with a loop, you might launch tens of thousands of CUDA kernels. Everything is controlled by the host. On TPU, it's completely different. You have one binary that you load to TPU. You DMA data for parameters to the CPU, and you tell TPU, go and run. And then sometime later, TPU does interrupt and tells the host, OK, I'm done. You can take data back from this device address, and you can DMA it back to host. So there's a huge distinction in how to program TPUs. TPUs can do callbacks back into host, and there is no really an efficient way from GPU to make the callback to the host. So GPU can't ask the host to do something and wake it up. On TPU, it's very easy. So TPU can block execution, ask host, for example, that's how host offloading work and collectives that go through DCN. TPU interrupts, ask host to do something, and host wakes up TPU, and TPU continues. So the host runtime. So there are so many things called runtime in XLA. So PGRT is the user visible runtime, but this is the runtime for frameworks. That's how frameworks like JAX and PyTorch target XLA. And PGRT runtime hides all the complexity of managing local devices. And also we have IFRT, another runtime API, but this is the runtime API that allows high-level frameworks to target multiple devices through a single API. It's for distributed execution. And XLA runtime is very like the lowest part of the stack. So PGRT, IFRT, the highest part of the stack, you have compiler paths in the middle, and then you have XLA runtime in the bottom. So on XLA CPU and GPU, we have thunks, basically unit of execution. You can imagine that XLA runtime is kind of an interpreter that has a small set of commands, and XLA interpreter executes this small set of commands one by one. So kernel thunk takes compiled kernel fusion and launches it on the underlying device, GPU, CPU. Or reduce thunk does collective operation. So it's NICO on CUDA, GLU, MPI, or some in-memory collectives, our internal collectives over DCN on CPU. While thunk, if thunk, control flow, for example, on GPU, while thunk implemented as you launch a sequence of kernels, you transfer the predicate back to host, and then the host decides, should we continue the while loop iteration? And the same for case conditionals. They call the same conceptually, very similar, but the very big difference that on GPU backend, everything is executed sequentially from a single thread, host thread, because you don't need multiple host threads. CUDA, stream, and GPU device takes care of concurrency. On XLA CPU, thanks is a data flow executor largely based on original TensorFlow ideas, because you have to use multiple cores to execute operations concurrently. Essentially, DAG of parallel loops with asynchronous callbacks and continuations, and we try to never block on CPU. XLA TPU runtime, called TPU system in the code, and it provides an API for launching programs on TPU and moving data. So it's much bigger than that, but the four most important functions. So you have some program source, which is assembly, TPU assembly, encoded in some binary file. You take the TPU assembly, you load the program into the instruction memory of the CPU device, you get back a program handle, and then you can execute program handle with buffers for arguments and buffers for results. And then you can transfer data from your host memory to some buffer on device, or transfer it back. So this is an implementation detail of the PGRT TPU client. Open source users don't see it. Maybe some part of that will be open source later, but it's not really important because all the open source users, they supposed to target TPUs with PGRT TPU client, which hides all of the details. So PGRT TPU client roughly has the same API. You have execute, compile, which gets you compiled PGRT executable, and then you can take a compiled PGRT executable and load it on device, which for CPU corresponds to load program, and then you get back an PGRT executable that you can execute with PGRT buffers. But that's all hidden. But conceptually, the idea that we don't really have runtime like thunks for CPU and GPU, because the host does almost nothing. It has a single program that is loaded in device and then executed completely on CPU up until the end. I think this will all be hidden from you. So you have PGRT API, and when you execute PGRT executable, you get back multiple futures for every output. And XLA itself internally can populate that future immediately when the data is available. And I think that's maybe what XLA does today. So XLA doesn't have to wait for the completion of your program. It can start the DMA early, and then it will mark the future, PGRT future, as complete. And that's when you get access to the data.
I see. But is there an API for me to know that, OK, this chunk of computation finished? Then
you get back the vector of futures, and you can do the future on-ready callback. And that's when you will be notified when the future will be resolved.
I see. Is there any instruction that I can?
No. Yeah, so nothing that is not inside PGRT public API. Yeah, so PGRT public API is the only official API that we provide for programming TPUs these days.
Gotcha.
So we'll have more. I think like Mosaic, for example, Pilot's Mosaic gives you low-level access for writing kernels, but still it doesn't help you with like PGRT level. So we expect that most of the users should go for PGRT, and that should be enough. And this is the abstraction that we provide and guarantee some backward compatibility. Yeah, so the relationship between PGRT runtime and XLA runtime. So PGRT is not really runtime. So PGRT is an API. So first of all, this is a C API with backward compatibility guarantees and stable ABI. So some binary protocol that you can implement and load PGRT as an object file compiled with a different toolchain. This is an API for frameworks. XLA runtime is low-level implementation detail of XLA backend that no one really should know about. So unless you're debugging some performance issues and curious how exactly kernels are executed on the underlying device, you shouldn't really know about XLA runtime. So at compile time, XLA compiler produces an executable, and executable has a requirement. So to be able to execute this program, you need to pass n buffers for arguments, m buffers for results, and 1 buffer for temp location of this particular size. So what happens, you just have to pass an properly aligned buffer of X number of bytes to XLA, and then XLA will assign different temporaries, intermediates, to different slices of the temp allocation at runtime. Yeah, so you have schedule, you have memory assignment, and based on your schedule and memory sizes, because everything is statically known at compile time, you know your peak memory size. Basically, the peak memory size of your temp allocation is all the values that are alive at given program point. And then you have some conflicts, memory alignment requirements, things like that, but all of that can be computed statically. This is probably a bug, because XLA should be deterministic. So if you run the same hardware, the same input program, XLA tries to be deterministic. Yeah, because I don't think there is any reason to be non-deterministic in this case. You have static schedule, memory, you do memory buffer assignment based on the schedule, and from that, you know your peak memory size and fragmentation. Yes, I think maybe hardware requirements, like alignment might be slightly different, things like that. Maybe slightly different fusions will create more HLO values, more live HLO values will increase the peak memory usage. Fragmentation can get worse. So yeah, you can't expect portability between TPU generations, because fusions will be different, layouts will be different, so the amount of padding might be different.
The context is that all those runs on the same hardware. We succeed.
Okay.
Some success, some so.
This is probably a bug in XLA then, because like same hardware, same input HLO, it should always produce the same output if other flags are the same. So if you see non-deterministic output, then this is clearly a bug in XLA. JAX doesn't see these constants. So yeah, so if it will be a constant inside trace function, it will be all constant folded. But if it is outside JAX JIT, to JAX, this is the runtime parameter. So yes, so we're working on auto-tuning right now, and we have some good results, like things for reduction. So what we do for CPU, we auto-tune LVM flags, loop unrolling, vectorization, how aggressive to do the unrolling, vector width, things like that. So we plan to do more and more auto-tuning for XLA CPU. And also XLA GPU. So the plan for XLA GPU is to do offline auto-tuning. So you have the database of all the fusions, all the kernels that you might want to compile. You run giant pipeline offline, you build a database, and then you can reuse it at compile time. And we're working with XLA GPU, so we will have the same APIs for auto-tuning and the same database for XLA CPU and GPU. So the idea that you shouldn't be doing auto-tuning when you compile things, because it is expensive. And for example, for online serving, you don't want to load new model and do auto-tuning while you do serving of the user requests. So eventually, we want to do auto-tuning based on the cost model, or auto-tuning based on some offline database of good decisions. Yes, so the idea that you have fusion, and for example, in XLA CPU, we have integrations with 1DNN, XNN pack, and we can emit LVM IR directly, and we want to auto-tune between different backends, so XLA CPU backends. And the same on GPU. So on GPU, you can call cuBLAS, you can call cuDNN, you can use Triton. So right now, the idea that you do fusion, generic fusion, and then you apply auto-tuning to generic fusion, and auto-tuning assigns fusion backend to your fusion. So custom call is if you have some coarse-grained operation in your input program, and you wrote it by hand in C++, and you want to plug it into JAX, you go to JAX FFI, and you write a JAX FFI custom call, and then it will be the custom call in HLO. But if you want a custom backend, this has to be done in tree. So custom calls, they can be done in your code base. You don't have to touch XLA. If you want to have a custom Fusion backend, that will require some changes in XLA. So we can make it customizable through some C APIs and try to provide some compatibility, but that's mostly an implementation detail of XLA. So if you go to the history, in the last week, we submitted a couple of patches that implements custom fusion path that fuses dot plus operations after dot. And then the idea that we want to reach that path for XLA and 1DNN. Basically, graph API. So if you have a fusion, you can emit LVM IR for your fusion, or you can emit graph IR of some library. So XLA has a graph IR, 1DNN has graph IR. I think we are out of time. Thank you, everyone.